In this video, we're going to talk about vector notation and also the standard unit vectors I, j, and k. You might be wondering, what is a unit vector? A unit vector is a vector that has a magnitude of 1 and its purpose is to give direction to another vector. So here's the typical formula of a unit vector. The unit vector is equal to the vector itself divided by the magnitude of that vector. Now let's say we have some vector v. That vector has an x component, vx, and a y component, vy. Whenever you see this arrow on top of a variable, it tells you it's a vector. Now, vx, the x component of v, is v cosine theta. And the y component of vector v is v sine theta. Now, we can also represent the vector v in terms of the standard unit vectors I, j, and k. So let's say this is the x-axis, the y-axis, and the z-axis. And let's say each of these blue arrows have a length of 1. The standard unit vector I has a length of 1 in the x direction. The standard unit vector j has a length of 1 in the y direction, and k has a length of 1 in the z direction. These are the values for I. It's 1, 0, 0, where this is x, y, and z. For j, it's 0, 1, 0, because it goes in the y direction. And for k, it's 0, 0, 1. Now the vector v, we can express it in terms of the unit vectors I and j if we have a two-dimensional vector. And we can also write it this way. We know vx is v cosine theta, and vy is v sine theta. By the way, when you see v in absolute value, that represents the magnitude of v, which in this case is going to be the square root of vx squared plus vy squared. So this is for two-dimensional vectors. But what about if we have a 3D vector? So let's go back to our 3D coordinate system, where this is x, y, and z. So let's say we have the vector v over here. So this vector has 3 components instead of 2. And that's vx, vy, and vz. Now, when dealing with three-dimensional vectors, you don't just have one angle, theta. You have 3 angles you need to consider. The first one is the angle alpha. Alpha is the angle between the x-axis and the vector v. Let me use different colors. So that's the angle alpha. Next, we have the angle beta, which is between the y-axis and the vector v. And then gamma is between the z-axis and the vector v. Now, Vx, the x component of vector v, is v cosine alpha. Now, of course, this is an absolute value. If I don't write an absolute value, just know that this is the magnitude of v. It's v cosine alpha times the standard unit vector I. Now, Vy is v, not sine, but v cosine beta. So it's a different angle. And Vz is going to be v cosine gamma. So if you have a three-dimensional vector, you need different formulas to calculate Vx, which is v cosine alpha, Vy, which is v cosine beta, and Vz, which is v cosine gamma. Now let's talk about the dot product formula. Let's say if we have two vectors, vectors A and B, and they're separated by an angle theta between them. If we want to multiply these two vectors, we could use the dot product formula. Whenever you use the dot product formula, you're going to multiply these two vectors, and the result will not be a vector quantity, but a scalar quantity. And remember, a scalar quantity is one that has magnitude but no direction. A vector quantity has both magnitude and direction. So the result of the dot product formula will give you a scalar result. So the dot product of A and B is going to be the magnitude of A times the magnitude of B times cosine theta. And this is equivalent to ax bx, so you're multiplying the x components of each vector together, plus the y components, the product of the y components, plus the product of the z components if it's a 3D vector. If it's a 2D vector, you could just focus on this part of the equation. Z would typically be 0. This part will be 0 for a 2D vector. Now you might be wondering why I decided to bring up the dot product formula. Because when dealing with the standard unit vectors I, j, and k, sometimes you need to know what the dot product of these vectors are. So I times I is going to be 1. J times j, using the dot product formula, is also 1. And k dot k is 1 as well. So anytime you multiply two identical standard unit vectors together, it's always going to be 1. If you're multiplying standard unit vectors that are different, using the dot product formula, it's going to be 0. So I dot j is 0, j dot k is 0, and I dot k is 0. And you could verify it with this formula. I'll give you some examples. So let's prove that the product of I and I is 1. So let's call this I1 and I2. So I1, we know it has the values 1, 0, 0. The same is true for I2. This is x, y, and z. Well, more specifically, if we associate A with I1 and B with I2, this would be AX, AY, AZ, and this will be BX, BY, BZ. So using the formula AX times BX, that's going to be 1 times 1. The y components are 0, so it's going to be plus 0 times 0, and the z components are 0. So this will end up being 1. So the dot product of I and I is always going to be 1. Likewise, for j and j, it will be 0 times 0 plus 1 times 1 plus 0 times 0, which is 1. Now let's show that I.j is equal to 0. So for I, we know it's 1, 0, 0. And for j, it's going to be 0, 1, 0. So let's say this is ax, ay, az, and this is bx, by, bz. So ax times bx, we have 1 times 0. Ay times by, 0 times 1. And az times bz is 0 times 0. So this ends up being 0. So anytime you take the dot product of two different standard unit vectors, it's going to be 0. And for two identical standard unit vectors, it will be 1. Now let's go over the vector cross product formula. So A cross B, you're multiplying two vectors using the cross product formula, and this will give you not a scalar quantity, but a vector quantity. The magnitude of this new vector quantity, which let's call it vector C, is going to be the magnitude of A times the magnitude of B times sine theta. And then we're going to multiply it by the unit vector of the position vector. Or let's say the unit position vector, r hat. So recall that a unit vector is basically any vector divided by its magnitude. If we multiply both sides by the magnitude of v, we get that vector v is equal to the magnitude of v times the corresponding unit vector. So any vector is basically the product of the magnitude times the direction. And that's the purpose of the unit vector. The unit vector will give the vector v its direction. So let's call the result of the cross product of A and B, which will give you a new vector quantity. Let's call that new vector quantity C. This part here, the magnitude part, is AB sine theta. That represents the magnitude of this vector. And this part here, the unit vector, will be equivalent to the unit position vector. So when dealing with the cross product formula, just know that this gives you the magnitude of the resultant vector quantity, and this gives you the direction. By the way, for those of you who want a printout of all the formulas that we talked about in this video, plus additional formulas that I'm not going to cover in this video, I'm going to post a link to a formula sheet with these formulas in the description section below this video. So if you want to get a printout of those formulas, feel free to take a look at that when you get a chance. R hat is the unit vector of the position vector R. Now the position vector R is basically, in unit vector notation, Rxi times the y component of, plus the y component plus the z component divided by the magnitude of R, which for a 3D vector is going to be Rx squared plus Ry squared plus Rz squared. For a 2D vector, you would just get rid of this, those two parts. Now, if you want to calculate the x component of the position vector, it's simply xv minus xa. For Ry, it's yb minus ya. And for Rz, it's ZB minus ZA. So let me show you that to you in another way. So let's say this is X, Y, and Z. And here is the position vector. Let's call it RAB. Now A will typically be the origin. It could be a point other than the origin, but typically it's the origin. And B is some other point. So going from A to B, we can get the position vector. So point A has the coordinates XA, YA, ZA. And point B has the coordinates XB, YB, ZB. So to determine the position vector, you just need to take the difference between XB and XA. That will give you the X component of the position vector. And then YB minus YA will give you the Y component. And then ZB minus ZA will give you the Z component. So that's how you could determine the position vector in unit vector notation. And then once you have that, you can determine R hat, the unit position vector, using this formula. I may have to rewrite this formula real quick. So in addition to this form of the cross product formula, there's also another form. You can also determine the cross product of two vectors by finding the determinant of a 3x3 matrix when it's written this way. So here we have the standard unit vectors I, J, and K, and below it AX, AY, AZ, and then BX, BY, BZ. Now this is equal to the Y component of A times the Z component of B minus the Z component of A times the Y component of B. When you multiply the Y and Z components for vectors A and B, this will give you the X component. And let's say this all equals some new vector C. So this represents the X component of C. Now there's more. Next we're going to multiply the Z component of A times the X component of B minus the X component of A times the Z component, not the Z component, but yeah, the Z component of B times the unit vector J. And all of that is going to give you the Y component of C. So when you multiply the Z and X components of vectors A and B, it will give you the Y component of C. And that's the basic idea behind the cross product formula. When you multiply two vectors, especially if they're perpendicular to each other, you get another vector that's perpendicular to the original two vectors that created it. Now for the last part, we're going to take the X component of A and multiply it by the Y component of B minus the Y component of A times the X component of B. And this will give us the Z component of the new vector C. So the result will be a vector quantity which we'll call vector C. So that's the result of using the cross product formula to multiply vectors A and B. Now, if we were to take the cross product of the unit vector I and the unit vector j, what will we get? It turns out we get the unit vector that's perpendicular to I and j, which is k. And you could verify that with this formula, which is going to take some time. So I is 1, 0, 0, and j is 0, 1, 0. So we'll associate this with A and this with B. So AY, this is X, Y, Z. AY is going to be 0. BZ is going to be 0. AZ is 0. BY is 1. Next we have AZ, which is 0. BX is 1. Here's, actually no, BX is 0. This is BX. AX is 1. That's AX. BZ is 0. And then AX is 1. BY, this is BY, that's 1 as well. Minus AY, AY is 0. And BX is 0. So hopefully I plugged in everything correctly. So this is 0 minus 0. So we have 0i. Everything here is 0. So that's 0j. Here we have 1 times 1, which is 1, minus 0. So we get 1k. So this is 0. Basically, that's nothing. We end up getting k. So the cross product of I and j is k. And you could use that formula to verify it. So I cross j is k. And there's an easier way to remember this. Let's say this is I, j, and k. So when you multiply I and j going in the clockwise direction, it will give you k. And if you multiply j and k, so starting with j, we're multiplying it by k, it's going to give us I. And if we start with k, multiply it by j, so we're starting with k, actually wait, I take that back. After k is I, so we're starting with k, and then we multiply it by I, it's going to give us j. So k cross I is j. So anytime you go in the clockwise direction, you're going to get a positive result. If you go in the reverse direction, it'll be negative. So instead of I cross j, if we do j cross I, it'll be negative k. So in this case, I'm starting with j, and I'm going towards I. So notice that I'm no longer going in the clockwise direction, I'm going in the counterclockwise direction. When I do that, it's going to give me k, but it's going to be negative. And you could use that formula. So I cross j is k, but if you reverse the order, j cross I will be negative k. Likewise, j cross k is positive I, k cross j is going to be negative I. So for that, I'm starting with k, I'm going to j, and I'm going to get I. But I'm going in a counterclockwise direction, so instead of getting a positive result, I'm going to get a negative result. Likewise, I cross k, so I'm starting with I, going towards k, and I'm going to end at j. But this is going to give me negative j since I'm going in the counterclockwise direction. So this system will help you to remember what results you should get when you're using the cross product formulas on the standard unit vectors. And of course, you could confirm each of these with the cross product formula like we did with the first example. Now, there's some other things that we need to talk about. So if you recall, when we took the dot product formula of two identical unit vectors, it was 1. And when they were different, it was 0. Well, the reverse is true for the cross product formula. If we take the cross product of two identical standard unit vectors, it's not going to be 1 as it was with the dot product formula. It's going to be 0. So I cross I is always 0. J cross J is 0. K cross K is 0. But whenever you cross two different standard unit vectors, you're going to get the other one, the third one. You just got to figure out if it's going to be positive or negative. And that circle system that I showed you will help you to determine if it's going to be positive or negative. So if you're doing J cross K, you're going to get the other unit vector I. You just got to figure out, is it positive I or negative I? So that's basically it for this video. I want to make sure that we covered the standard unit vectors I, J, and K, and you know the formulas associated with these if you need to take the dot product or the cross product of these unit vectors. So don't forget to check out that formula sheet for those of you who want to print out of these notes, and thanks again for watching.